So we optimize the protocol, and just to check that how close, so then we calculate the power, maximize it, and calculate the efficiency at maximum power in the earlier example. And here I just show that how close we can be to Kurzov-Alborn limit. That's what the macroscopic engine shows. So this line, maybe I give it a change. But how to? So this line is the Kurzov-Alborn line, this dotted one, and then we started for various ratios of this. We have a protocol, right? That we optimized and get. So they have some parameters. That is the maximum value of the protocol, minimum value of the protocol. This two ratio, that's our hand that controls the jump, right? The difference of those things. So keeping the difference same, we can change the ratio, maximum versus minimum, right? And by changing the ratio starting from this to this, and so this A is some fit parameter. So A comes as, with this we can actually go quite close to this with this thing, Kurzov. But anyway, this is the reminiscent of the last thing.
What is the expression for the?
So 1 by root over Tc by Th that I derived yesterday. So now this one, this particular lecture I briefly introduced the most, I would say, the kind of very recent topic that there was a colloquium by Rajesh yesterday. So that is active heat. So the basic idea is, so far we have heard the environment, the bath is thermal, it is thermally equilibrated at temperature T. Right? Now, what happens if I replace that bath with some non-equilibrium bath? Say I have some bacteria or some Young's particle, self-propelling and all. What happens to our engine? Right? So that is the question. But I should, so it is obviously there that this question is not only like engine. Of course, we work on the microscopic heat engine and all, but this brings a huge amount of all the questions, because right from the beginning, the derivations of stochastic thermodynamics, the fluctuation relations, the microscopic reversibility condition, etc., everything is built on something called detailed balance, or in the jump process, Abhishek showed it is a detailed balance or generalized detailed balance, which is there in the Lucas book. Or if it is Lajva equation, then we have something like the noise strength is equal to 2 gamma kBt, the fluctuation dissipation relation. So what is detailed balance or generalized detailed balance in jump processes or discontinuous processes, stochastic processes? The same role is played by this noise strength is equal to 2 gamma kBt relation in continuous stochastic processes, Lajva processes. Moment you replace your bath, which was in equilibrium, by some active bath, those relations are no more. You can't use those relations. Detailed balance is gone, fluctuation dissipation relation is gone. Okay. Now the set of derivations that you did, the fluctuation relations basically, then this thing, they are in question. they will not be, so you have to rewrite those things. Now, not yet done those part as far as I know, that part is not yet complete. But the point is, even if
complete means in this course or
no, it is not there. It is. It is up to them to complete. It is maybe up to them to complete. I don't know. Anyway, but then point is, even if those things are not there, not solid, but one can still define in a model-based way, not generally maybe, what is my stochastic work, what is my stochastic heat, what is my stochastic internal energy. And based on that, those definitions, one can at least proceed towards making this so-called active heat engines. That means the replacing the thermal bath by some active bath. Okay. So now that's what we're trying to see. So, but keep in mind that those basic conditions are now shaky condition, like they are not very solid anymore because I. Yes.
In the Gardner equation, with this theta noise, if I have this active noise as well, which is like exponentially growing.
Yes.
So wouldn't it be like similar to like having an active bar, like thermal bar?
Yeah, true. Yes.
Can it not be so like?
No, the problem is you see that the Markovianity is gone. Like in the very basic principle that Abhishek showed, when you write the forward path probability and the backward path probability, then you chop every, like the whole thing with two-step process, right? x0 to x1, x1 to x2, independently you multiply all those transition probabilities. That step you can't do anymore. The very basic step was stuck. Right? So that's the problem. But given that, we can't define from, as you mentioned, the example that you mentioned with an exponentially correlated noise and all non-Markovian noise, we can, but for that particular model, we can identify what is heat, what is work, what is internal energy. Right? So that part is done. But now if you have some bit complicated noise structure, like active systems can have many other details. So then also you have to rethink that again, what is noise, what is heat, what is work, and what is internal energy. So that's what it is now. So I will exactly take that model that you have mentioned, an exponentially correlated noise, and to try to motivate how to define heat, energy, etc. engine. Okay. I will not go details of this, but I will show a little bit of steps. So basically, that model that you mentioned, it is motivated. It is actually written in a paper by Lecture-4. It is 2000 PRL paper, 2000. I guess the. This is a very good, means readable and just go through this paper. PRL volume. So this is an experimental paper where the experiment by Lecture-4, and the experiment was like that. So they took up 0.4 micrometer, I guess. No, sorry, 0.4 centimeter. 0.4 centimeter. So they took a soap film. So this is like 0.4 centimeter. Okay, and there they have some bacteria, and they measure the diffusion coefficient. Basically, it's very versus x square average. Simple as that. So the soap film is stabilized and all, but the paper is nice, like so there, what they essentially get is like this. The main result of the paper is this graph. So delta R square average versus time, and roughly just sketching. So this goes as e to the power alpha, where alpha is close to 2 here and alpha is like 1. And this time scale is 10 to the power 0, that is 1 seconds. So this is what their main result. The diffusion, how the bacteria diffuses in a soap film. So from there, they concluded this. Okay, wait. I was wrong. So this bacteria. No, I was wrong. So there is bacteria everywhere. Sorry. So there is a polystyrene bead. Actually, yes, PS. This polystyrene bead. Yeah. So this is like quote the diameter. It's important. It's like micron order, but so this is a micron order bead, polystyrene bead, and there this R square is this, like the delta R square average of this polystyrene. Bacteria is in background. Bacteria is in background.
In that soap film.
And so they have checked lot of things, lot of care, like the micelle density and all, whether they can influence the bacterial motions, or a lot of different checks are there. So it's very nice paper, detailed. And there they mentioned that this graph actually motivates them to directly write the equation of motion of the polystyrene bead. So that was like
the kicks for the movement are coming from the bacteria, not the film.
both are there. Like, of course, there is fluid, so no one can stop the fluid particle to kick them. But bacteria's kicks are also there.
But here the particle is very big compared to.
That's what I wanted to quote this size. Now I forgot. But
5 micrometers.
5 micrometer kind of, yes, exactly. So this
bacteria is one
bacteria is
same size,
more or less same size, right? Okay. So then,
As the bacteria is
so the bacterial kick is the most important. So this 2 two things was important. So they first write this equation, which has some importance. I will mention. So this noise is there.
The density is also very important of the bacterial bath. Like
In the bacterial density is
if it breaks first, shouldn't you see like alpha equals to 1 and then some superdiffusion?
in the ballistic and all.
No. This is already ballistic
Ah.
because of the bacterial bath, but even shorter time scales. If like
So density is just, if to quote it, I find this one, 5.4 into 10 to the power 10 cells per centimeter cube, which is like 10% of the whole volume. So this was the whole volume in this. So this is the thing they quote in the paper. It is quite low. It's
Crossover time speed
1, roughly. This is 10 to the power 0.
1 second.
1 second in second. Yes. So there are, okay, now, so there are size dependence also on the bit. So they took two different size, and this is alpha is equal to 2, and then for this is for bigger, and if it take lower, so this is like 1.5, but still greater than 1. Okay, and this one is same for both. Okay, so there if you go lower side of T, the size dependence also is there in the alpha. That's what they mention in the paper. So I just
Does the crossover time also depend on the size?
they say it's not, at least from their paper. So and there's the standard GFE measurement and all. Okay, I was writing this equation. So this, their observation actually motivates them to write this equation directly. So this F is noise, 0, and F 0 D average is 4 D gamma square. The model they use. Okay. So, and the time scale, the inertial time scale, which is much, so this was at 1 roughly, and this was at 10 to the power minus 5 to the power minus 6, but the inertia, this microsecond it takes to decay the inertia. So whatever we are getting here is not due to inertia. That was the point. Okay. So if you have bacteria in your this thing, then the behavior, the ballistic behavior you may get it from inertia also, you may get it from bacteria, but you, in case of the inertia thing, that decays here at most 0, because 10 to the power minus 6 microseconds. So this whole time scale, the ballistic behavior, almost like close to ballistic behavior, is due to bacteria. That is clean in this paper, okay, from their observation. So you can just drop this down here.
Arnav, a little clarification that the soft film, you say that whether bacteria is living, whether it is also changes with due to the movement of the bacteria on the film, because it may happen that it will.
No, it was stabilized. It was stabilized by some chemistry, which I don't understand properly, but there are some. You may go through. It is there is some. Okay, I have quoted. This is something called some protocol they have used. Which is very. It seems to me it is very common protocol in this kind of experiment. So this is some kind of non-ionic.
Even because the elasticity of
Bacteria will also be moving, right?
Yeah, of course.
bacteria is moving on that film, so it may, due to the elasticity of the film, it may keep the colloidal particle.
Oh no, but what you said there is there is no elasticity of something. It is viscous.
No,
The medium.
It is the colloidal particle put on the soft film. So it may happen that due to the movement of the bacteria, there is some change in the that curvature or so.
No, bacteria. I don't think they are not that big.
Surface film.
They are not. So what you typically when we see some kind of film, the surface tension and all, it's like quite big stuff, like flies and all that we see. But bacteria is too small for them to. I think so.
Okay.
Can you define why you drop the degree? Why you drop the degree return?
That is it's purely due to time scale. Like the inertia thing that the momentum get balanced or equilibrated within 10 to the power minus 6 second or 10 to the power minus 5 second at most. Now this is what?
How do you find it?
So there they have measured actually in the paper that you will find, because your time scale, your friction coefficient, this gives you the time scale of this thing, that is, and also this m by gamma and all. So from there you actually see this, the momentum thing is decayed within microseconds, but this ballistic behavior continues till 1 second. It's huge. That is why. That's it.
Why after 1 second become diffusive? After 1 second, why become diffusive? After 1 second, bacteria dies from.
No, that is correlation. That's TC. That's this. But TC, no. But it is TC, of course. But I'm thinking about point of view of experiments. Like, unless the experiment is there, how can I? This is a model. That is from the. So TC, I will put this 1 second. It is there, but this comes after the experiment. From experiment to why.
You can interpret with the kicks from the bacteria. It is decorrelated.
It is decorrelated. That is what the explanation.
After 1 second.
Yeah. So after a certain time scale, like this is 1 second. That all the kicks that they become.
So usually
There was a correlation, exponential correlation. That correlation decays exponentially. That is why this model is. So it is not like this model is there. That's why this experiment. The experiment is there. That is why this model. It's not the other way around.
Related to so hydrodynamic effects.
They haven't considered yet. They didn't need it because they didn't observe it. So this is what. So now. So now taking this model, so we are just thinking, if we try to write the first law. So whatever we have written in the Gaussian white noise, the first law, very similar way. We don't have to use any statistics there. What we will do, so there is, okay, first, to begin with, so this is what their model experiments. Now one can have this, let's say I have a potential optical trap or something in this system, and let's say you have this gamma x dot minus some u x del x is t, and then you have f with this set of correlation. Same trick, we'll put this x dot, okay, this plus minus f So this is coming from, the logic is same, like this is this thing, the noise as well as the friction, they are coming from the soap film, the bacteria, right? So we can, from that motivates me to put this in the heat part. Exactly similar, at least in this setup. And then rest is here. So from there, I will split this into two terms. One will be internal energy, as we did earlier, and other will be the work. This will be the heat. Exactly same way, but this is motivated by this thing.
Sorry, I missed. Where is the del U came from? I missed that.
In this experiment, there is nothing such. So we can now think of putting some trap in this setup.
Putting additional force.
Yes, putting additional force, then reading it, as we did last time. But I am again concerned that this noise for this particular case, yes, okay, this can be well motivated by these experiments. But recently we were discussing also in also other many cases, some cases at least, it depends on the structure of the statistics of the noise, whether we can really put into it everything, the beat or some part of noise can be included into work. So those kind of confusion remains. It is there. Okay. Yes.
So I think I remember this friction coefficient, if the noise is correlated, this doesn't have the convolution with the velocity. Is there a reason for that?
No, no. Why you need convolution?
It's still dependent the friction coefficient.
Wait.
Because the noise is correlated, usually in like generalized random equation, correlated means the friction has a.
Oh, you mean this term?
So in the friction coefficient, so gamma T minus tau integrated from 0 to T.
Oh, okay, correct. Good point. So this you mean the generic equation should be written like as I think Rajesh is kind of shown. This one. Are you talking about this? So this is what I.
Yeah.
Yes. This is what you are thinking of, right? And then you have this correlation. Okay. This is viscoelastic thing. That now gamma decays, the friction current decays with some correlation times say Tc prime. In general, it can be like that, and this decays with Tc, the noise correlation. When this Tc is equal to Tc prime, then something called generalized fluctuation dissipation relation or Kubo relations, they are valid, okay, and you get back your equilibrium numbers. Here it is not. Here in general, in this particular in presence of bacteria or any kind of active systems, active particles, this Tc is not equal to Tc prime. And we are taking an extreme case where this particular Tc prime tends to 0. And when this tends to 0, this gamma become delta function. And this gives you d of x. Correct? So this e to the power minus mod x by tau 1 by tau limit tau tends to 0 is your delta x. This is another representation of delta function. Okay. So this is the. So we had an equilibrium thing when only Tc is equal to Tc prime, giving you the Kubo relations. But we break the detail balance here, making Tc is different from Tc prime. And this is an extreme case where this Tc tends to 0. Clear? So this part is, so u x t, du is del x. So this is the force coming from bath multiplied by the velocity, giving me the power. I have to multiply this side as well. Del x into dx dt. This one I will write it as like the differential form. Del u x this will be my my heat per unit time. This is my internal energy. This is some this is the work. So if I integrate once with time, just check whether it's correct. Start. Left hand side dt is.
You do dt to right the left hand side you have divided by.
Oh no, this is q by time. That is. So this way we can now. So this is the first law in this particular case. Okay. Let's. So having said this first law, we thought of a kind of experiment that we say we take this setup, okay, and then we have this trap. We will run it with cycle like expansion, then compression. And what we will do, the activity of the bacteria in the first half when it is expanding, we will keep almost zero, say. Chemically people can do that. The first half when it is expanding. And when it is contracting, then we switch it on. I mean, the activity can be switched on. We will not do anything with the temperature. So the soap film, the temperature, if means you put a thermometer here, you will get some number. That number we are not going to change. We will not heat it up or cool it down. Okay, let's see what happens. So what I am going to do now, I will run a cycle. Okay, the cycle is like we have a trap. So first it will expand, then it will contract. No jump, nothing. Okay, first expansion, then compression, and it will come to the same point to maintain the cyclicity. That is in our hand. We can control it. On top of
reversible.
Yes, I mean we can do both. I mean theoretically we can do both. The calculation what I will show here, it is a reversible path, simplest. We will not go to non-Poisson static or things like that. It will be complicated. First do the reversible path. Okay.
While maintaining the temperature.
While maintaining the I don't want to say temperature because it's a non-equilibrium film. That's why I say that I put a thermometer there. I get some number. I don't know what it is, but I will keep that number constant.
So here in this case, you said you switch off the activity.
Some chemical, like not with shining light or all, that may heat up the things.
But in the equations, what does it amount to?
That amounts to, I had somewhere correlation. Okay, I wrote. So in the expansion path, say this is the way I expand my K of T. Be very slow, reversible. This is my say tau by 2. Tau is the whole cycle, tau by 2 up to that. So this is 0. And this is my compression path. This is tau. This is my full cycle. Okay? Here the noise correlator is delta with this normal 2 gamma k b t. T means here it is all equilibrium, say that number. Okay, with thermometer. And here it is that like f d prime is that d whatever that
D gamma square.
or d gamma square. Then what was that?
E to the power by Tc.
By Tc to the power minus T by Tc. Now you may ask, what is my d here? There my answer will be this is this, but this number is my whatever number I get from the thermometer. Correct. And also I can directly put d there because they have measured it in experiments.
So you are planning to do it in the model?
Model, exactly, of course. So in the first half, this noise. Second half, this noise. This is how I introduce activity. It is absolutely motivated by their experiments. Clear?
So here there are two things here. For example, if you make the noise more correlated, okay, which means Tc is large, then the strength decreases.
Which strength?
The 4D gamma square by Tc.
But the whole thing may not, because Tc is
The integral remains, I think, constant. I think if you do an integral from 0 to infinity, I think that will not depend on TC.
TC tends to 0, yes. TC very large. Let me see what we got.
No, the only reason I'm asking is this, is that, for example, there is a strength of the noise. And how do you compare the strength of the thermal noise and the strength of the activity?
It's different. See, the thermal noise is 2 gamma kBT, right? Why? Because there is no, so here, this function, and there is my delta, right? T minus T. Now, why this TC comes?
Right, there's a delta as a unit.
Delta has a dimension of 1 by T, right? That carries the dimension of 1 by T. Here it is not. The correlator is dimensionless. So you have some TC here, there. But here you don't.
Yes.
Right. So you are correct in that sense. So then let's see how to do some. Okay, so this is what we exactly wanted to show.
So I had a question. So you are increasing the activity and you are saying that the temperature of, let's say, we can't measure the temperature of this bacterial bar, but the fluid that you have, you are not increasing that temperature.
No. We are just.
I can't understand how to note, how can temperature be fixed, but still you are increasing the activity of bacteria.
Means by some chemical pathway or chemical ways, you just increase the mobility of the bacteria.
Yeah, right. So my question is related to that. That if bacterial motility will increase, so they are low in motion, so they will be influencing this other particles, liquid particles, and hence they will have more kinetic energy on the average than.
They may, but there are experiments also. It's like if you put some food there, they will be much more mobile, but you don't find that effect on the whatever. If you have some thermometer inside, it will show some number. That number will not change.
Okay, that could happen.
That could happen. Yes. So now, so there is another point. Actually, we see why we take this thing, because there is one parameter that controls the activity Tc prime. So what happens if I take Tc prime tends to 0, then both will boil down to same temperature and we should get 0 work out of it. Because in thermal limit, with same temperature, we need at least 2 temperature to get work out of it. So Tc prime, if I take tends to 0, then we should have our thermal limit the 0 work output. Correct? So we wanted to check whether we are getting there or not. So our thermal limit, equilibrium limit is there. So this is what we try to, so this paper is here. This one I was talking about, and then so with Rahul. So this was the protocol that we used, that the time dependence in strength. Actually, this protocol in the quasi-static case will not matter much, but we have also did non-quasi-static calculations, which we will not do here. But there the protocol matters. It's very simple linear protocol, nothing there, but we have to be cyclic. So Kmax came in at the maximum and minimum value of the protocols. Here nothing, no optimization is there. Okay. So no jump. We just wanted to check what is the effect of.
So audio control is TC. That's all.
Yes.
TC is
So
the
because
control
TC
variable.
will tell me this is your thermal limit at TC tends to 0, and if you larger and larger TC will give you the athermal or this active limit.
Has this been tested experimentally? Explicit.
This particular
this feature of correlation of
no, not yet. So then you do whatever that I discussed, this correlations and all, and this is the first law that I just explained there. So this is the heat part, this is the internal energy change, this is the work that I just explained. This is efficiency. I just keep. So this general part is a little bit complicated. I will not go there. And the special part. So particular case. So we just now I mentioned this is 1 by tau a exponential. This is t minus t prime by tau a. So if you take tau a tends to 0, you will say t1 is like 2 gamma kVt. So if your tau a tends to 0, you are getting delta correlated noise there. Okay. So just you get back, you fall back your thermal thing, and you will, if my thermodynamics is correct, then you have your 0 work output because there is same temperature. So then, so this, okay. Now, a lot of simplifications are there. So initially we took, as we changed this activity and all here, our gamma might change, gamma 1, gamma 2. So all those things are not required. I will not tell you. But this gamma, so a very special case where the gamma remains same here. It's gamma 1 here, gamma 2, gamma here, gamma here as well. Okay, it's a special case, that's why I'm saying. So now you can calculate in the quasi-static limit what is your sigma, or the in mind the earlier class notation it was omega. So x square average. X square average in first half, which is the thermal half, and the x square average in the active half. Okay, and this actually carries the information of activity. It's not very clear here. I don't know why it is like that. Yes. You see, moment I so this k of this is the protocol, but we are varying it very slowly. Okay, so there is a time dependence, but it is very slow. So while deriving this, actually what happened is k dot comes, and we say this k dot is constant or very slowly varying. So I take this out of integral and all. With this, with approximation, I land up on this. We land up on this expression. This is the sigma for thermal part. This is d1 is 2 gamma kVt. Here also like that. And here you see the tau a. This is the correlation time. So moment you put tau a to be 0, we are getting back the thermal width. Okay. So actually thermal width is decreased when you have this kind of activity, at least this kind of model. So sigma is that omega, that in the last class there was omega, no? That x square average. X square average. So that's what we need.
Sir, what is K1 and what is K2?
So K1 and K2 are the protocols that that is how the strength of the trap changes.
So when tau is 0, then we want this between K1 and
K2 is also there now, right? This 2 K2, so tau when tau is 0, it becomes 2 K2 gamma, which is the thermal width.
This is a confusion, right? I do not understand. That if you have colored noise, then will x square, right, omega, have a clear-cut expression?
So this expression is at large time scale, like when you this quasi-static limit. When this k is changing very slowly. But if your k is not at all changing,
Like, let us say it's constant.
Huh.
You have colored noise.
then you have.
Okay. Then you have expression for
Then
this.
you have a clean expression of this. This complication comes because I have a time dependent k. And then you can put this thing, once you calculate sigma, then you have everything, you have work, right? And you will get the average work, which is non-zero, and you see what is there. The limiting cases are very clear here, that tau is the correlation time. This is TC. So the paper's notation is a little different, but is TC there? This tau. And then you have this average work. What is x? X is again C. 2 gamma k naught, that is the constant coming up from the protocol, and tau a. So moment you put tau a to be 0, x becomes infinity, then this whole thing becomes 0. So log 1, 0, your average work output becomes 0. So you are in thermal part. Do you see it? But when, if tau a becomes very high, what happens? Highly active. Can we extract more and more and more work? That is also not the case. Then x becomes 0. This becomes a finite limit. This kVt half log. I don't know why it is so close to Zillard. I have no idea. Absolutely no idea.
For maximum activity, the amount of work
Is saturated. So it is not beyond carbon. This is the reason that it is not crossing carbon at any point. It saturates.
See, because there is, if you look at it, the total impulse that is given to you, impulse is a wrong word I am using. If you do the integral of the correlation function.
Now I'm
now
started thinking in this way. Maybe
it's
what you are
so
saying
you are
is
only providing certain amount of energy quotes unquote in the system.
because your mind the
Because it is
strength
spread over
goes
more
down.
time.
The strength goes down. You are saying one by t.
And the integral is the same for both.
Same for.
So which means that over the particular amount of time, this seems identical.
Maybe yes. So this is the maximum work that we can extract. That is where like everything like.
And that's exactly what I was asking you. What is the strength of the correlator? Because TCI is the only parameter. In principle, your coefficient can also be independent. It's that 4D TC, right? You could just keep what? Just completely separate. You call that some A.
Yeah, but so that is there. But then the problem is I don't have the. So I could have taken that, but my issue was like then I don't have the thermal limit. Somehow I have to switch off. At some limit I have to switch off the activity and get back to thermal.
So in principle you could have that and thermal.
And thermal. Right,
and then you make A to be equal to 0.
That is all. And well, so that I haven't done here.
No,
And that true also because again motivation is the experiment. They didn't took it. They took just this.
But there, as you said some time ago, that your thermal noise and active noise, for example, would be acting in tandem, right? Thermal and active collisions can be acting together.
Together, yes, that is
in
possible.
that sense, for example,
that is possible. That is possible. So that's what I say. There are many different possibilities so far. There is no unique description of this particular problem so far. But this particular model system, this motivated by this experiment, is giving me this. Now, this is the, again, this efficiency. That average work Almost. So average work versus average heat. Again, the same thing as it showed up in work, it showed up here as well. So we have a maximum efficiency that can be achieved, which is way below than Carnot. In fact, here Carnot has no meaning actually. It's like if I have the thermal limit is two temperatures are same. So unless and until I define some effective temperature, but which I haven't defined. So this is. So then the question was like whether I can get, how can we compare this system to a passive micro heat engine, whether it is better or this thing. For comparison, actually we have some other parameter. Let's go jump to this. So this parameter, I think in engine literature there is some name which I am now forgetting. Some factor they mentioned, but anyway, this is for passive heat engine which has two different temperatures as we discussed, and this N is the, so it is not necessary that we have this K here. This N is what? This is K0, this is K0 by N, and this is K0. So N is not necessarily 2, we can have a parameter there. And this N is here, this N, and in terms of N we can check the efficiency. So this black one is the efficiency of the active heat engine plotted with N, and the other three are the passive one for different, if I am not wrong, comparison for different this parameter Z. Okay. Z involves tau 0, K0, tau 0, K0 and gamma basically. So this is the dimensionless parameter with various time scales of the system.
Why was the red line behaving so differently?
Not red line, the black line.
The black.
The black line is the active part actually. So what our take our take was like at around whether active system is efficient or not, in comparison to passive one, whether it is more efficient or it depends on the parameter that we are using. It is not like universally one can say that active systems are more efficient, and at least for this thing. And the other point is the last talk, as far as I remember, this work, etc. They have shown that more and more work is obtained. Work may be more, but the thing is that efficiency, how efficient it is. Then it comes to that whether active system can be less efficient in some parameter space and can be more efficient than the passive counterpart in some parameter space. So it depends on which parameter space we are.
So this black one is a non-monotonic behavior.
Yes.
Which has an optimal value of rain for which
so far this model is saying. So this is the thing I just wanted to show related to yesterday. So this was in.
So in that graph, smaller the Z value, smaller the activity.
Smaller the activity, no, in efficiency.
Efficiency.
Yes. So this was another one which is much recent, where we use other kinds of noise, not only exponentially this one correlated. So this is the reference. So this one is the this is exactly solvable model, so we can do analytically all the steps. And there we have used different kinds of noise for activity, and we compare. So just wanted to show something here. according to yesterday's talk. So this is active particles heat engines, and we are using this kind of dichotomous noise, run-and-tumble motions, exponentially correlated, so two different kind of active noises and thermal noises. So there we can show some work distribution that yesterday, or X distribution. Here. So this is the X distribution, P of X, as yesterday also there was experimental this one, so it can be very, very non-Gaussian as mentioned. There are different, so this is RT means run and tumble, TH means thermal, then CN means color noise, okay, some color noise. So there we have, this is simulation actually. So we can calculate the X distribution for various noises, and we see this bimodality, all sort of complex functions as distribution of X in case of active systems. So this is what I just wanted to share with you. And
What is beta?
which one?
Beta.
Beta is a parameter there. It's not heavy. Something else. Yeah.
But I'm just trying to distinguish between run and tumble.
It's somewhere written here. Is a this one. So this is K, and this is coming from noise. So there's a competition between noise and this one. Strength of the trap. There's a ratio of this.
So yeah, what is the probability distribution in log scale, right?
Yes.
But is there any particular reason for doing that?
This is very generic. If you like to see some small differences enlarge and first thing that you see typically, this is not specific to probability distribution. It can be very like some power law behavior is like exaggerating.
Typically, if you have a Gaussian, it will be a bell curve.
Yeah.
And the non-Gaussian, you will see like deviations from the bell curve.
For example, this one is, I would say, is very, very Gaussian, the blue one, and these things, bimodality, etc., off from Gaussian.
Or normalized, normalized.
This is density.
So the conclusion, like Indonesia's talk yesterday, he said that one is the effective temperature, which depends on the variance of the
We haven't defined any effective temperature so far.
And other is the non-Gaussian, which will decide what is the efficiency.
So in some cases we are getting that, but it is not obvious for all the cases. It depends on what kind of noise we use, what kind of model we use.
So you cannot reduce it to two parameters.
So it's not
The efficiency of the model is not reducible to just two
two
parameters.
parameters. It seems to us like that's why we try different models.
Or kurtosis, like he said.
Good.
So,